Welcome to this special edition of Frequency Matters, the RF and Microwave Update series. I'm Pat Hindle, and today I'm with David Slack, Director of Engineering at Times Microwave Systems. Welcome, Dave.
Hi, Patrick. Thank you very much. Glad to be here.
So today we're going to discuss the challenges of the space market and designing products for that market. The commercialization of the space market, including new broadband networks and even space tourism, offers great opportunities for market growth. However, the space environment is very harsh for components and interconnects. David, what are some of the overall demands being put on products for space applications?
So in my view, it's reliability. I mean, you think about the history of the space program. The Telstar 1 was launched in 1962. It lasted 4 months before it failed. In the next 7 months following that, they lost 6 satellites. And they figured out they had a reliability problem, and there was a whole host of specifications and requirements. The qualified material list, the QML, was developed coming out of this, where you had your quality systems had to be certified, your parts had to be certified and qualified. A lot of paperwork, a lot of documentation, a lot of testing that went into that. They produced very expensive parts, but it worked. The reliability of the satellite program, just became very reliable and dependable. The billion-dollar satellites that they were putting up were flying and were working. So that was the start, and it has been predominant in the space industry for quite some time. More recently, industry and the scientific community have figured out that they could put up a larger number of smaller satellites that were much less expensive. At the same time, in parallel, industry in general, in response to offshore competition, have really upped their game on quality assurance and quality control in the business systems, ISO 9001, AS 9100, things like that. So the two have kind of closed the reliability gap to where there's a strong trend towards commercial off-the-shelf parts. So the need for these special QML parts is reducing, and the acceptance and risk tolerance is changing to accept commercial off-the-shelf parts. So that's a real big trend that I see, and I see it continuing and accelerating as we go forward.
Yeah, the commercial new space market has really shown that the quality is high enough that they don't have to go through that full screening anymore. So that's definitely reduced costs. So what are some of the most challenging failure mechanisms that need to be addressed in the cable and connector design?
So to me, I think about a satellite going through space, and that's the thing that most people think of first. To me, I really think about before you can fly in space, you have to get to space. So there's the assembly and integration process that happens on the ground, which is actually more severe and more harsh than you might imagine, with a lot of mechanical work going on, a lot of touch, a lot of people touching the parts. A lot of parts fail at that stage, at the integration stage, believe it or not. Of course, it can be corrected at that point, so it's not as severe, but it happens. And then there's the launch phase. Now, a lot of companies like Times, we supply product into the payloads as well as the launch vehicle, and the launch vehicle is just an intense environment. Doesn't last for very long, but it's a quasi-controlled explosion that might go 2 to 5 minutes or something. So vibration, shock, pyrotechnic shock, sound barrier things, So then you get to the flight environment itself, which mechanically, environmentally, it's actually kind of peaceful. It's serene, it's quiet. There's no buffeting from the slipstream and things like that. But what you have to live with there, and you have to live with it for years, is, and the big issues that I see are vacuum, radiation, and temperature. So those are really the key things. Vacuum it causes certain things to happen. Radiation is just not a friend of polymers and many in semiconductors and things like that. And temperature cycling is like doing a thermal shock on it multiple times a day after day for years. And that's, it's actually a pretty harsh environment right there.
Yeah, there's really big extremes between temperature. So what are some of the special materials and design techniques that are used to overcome these challenges?
So it starts with I think having a broad range of tools at your disposal. I mean, there's a difference between having the right product and an almost right product, and these are the things that I think allow you really to go towards a commercial off the shelf type philosophies by having just exactly the right product for the right part of the satellite for the right mission, things like that. So you know, we make flexible coaxial microwave cable assemblies. So we use a lot of polymers. Metals aren't affected as much for radiation, but we find that, you know, there's PEEK is a pretty radiation resistant plastic. Polyethylenes and you know, polypropylenes are actually not quite as radiation resistant, but are reasonably, relatively radiation resistant. And then because this is microwave journal, everybody listening to this knows that, you know, DuPont's Teflon is almost the perfect dielectric material. It also happens to be one of the worst as far as being radiation resistant. So depending on where you are, you might want to choose some non-traditional flavor of polymers and plastics. There's also inorganic materials, silica dielectrics and mica dielectrics, and you know, things like that. There's other outer conductors, you know, steel, thin stainless steel foils and things like that. Then it's the mechanical mechanisms, soldering and how you attach mechanical parts and matching coefficients of expansion very well so that they'll withstand that constant thermal cycling without breaking. I think success or failure really comes down to how well you understand the environment where that component will be installed in a vehicle. So super important to understand it.
So what future improvements do you expect over the next few years in the component space market?
Well, I think this is a hugely exciting time to be looking at the space market. I think historically speaking, around the turn of the 20th century, people were riding their horses and buggies. They were looking at these wealthy people driving their automobiles and shaking their head at people that had more money than they knew how to spend, and this crazy fad that people are doing for recreation because they can. 15, 20 years later, everybody's driving a car and shaking their heads at the people that are flying around in airplanes there was no market for it. There was no way to really make money at it. Military used them, and people with a lot of disposable income were just using them for recreation. And if you fast forward to last year, we started putting wealthy people with a lot of disposable income into space just for fun, just because we can. So you don't have to be a futuristic prognosticator to kind of play the cycle forward, right? It's going to be more and more common in relatively soon to see more and more people, more and more mainstream people in space. It costs about $10,000 a pound to put material in space. On the moon, there's a lot of silicon and magnesium, aluminum, iron. There's a lot of raw materials there. In the permanently shaded parts of craters, there's a lot of water there. There's a lot of liquid ice water. There's frozen methane, hydrogen. There's a virtual inexhaustible supply of sun power, you know, solar power there. So you take all of those things, put them in a mixing pot, and you throw in a little bit of artificial intelligence, smart robots, additive manufacturing, the ability to print filaments and actually print parts, you know, mechanical and structural parts, spars and ribs and things like that. I mean, I think we're going to see in our lifetime, we're going to see things shift from a space for Earth economy to a space for space economy, or at least we're going to add on that space for space. And what I mean by that is the space flight industry up till now has been, we put these vehicles in space for the benefit of people here on Earth, whether it's services or weather tracking or navigation, what have you. I see going forward, will put these vehicles in space to support construction in space, to support manned missions to Mars, to support the manufacturing of way stations along the way to Mars and things like that. Instead of lifting this material from Earth to space, we'll mine it, smelt it, refine it, manufacture it in space. And it's not crazy. It's happening. I mean, people are doing this. There's a company called MIS, which Made in Space. They have a Vulcan program funded by NASA. That's their mission. That is the mission of the company, is to manufacture in space for use in space. So I think the future is like really, really exciting. I'm on the edge of my chair. I'm leaning in, looking forward, just really, really dying to see how it plays out. I think it's going to be a really fascinating going forward the next, 5, 10, 20 years.
Well, thanks, David. I love your insights and I love your positive spin on everything. It's definitely an exciting market to be in, and Glad Times is supplying such reliable products there. So to our viewers, you can find out more episodes at videos.microwavejournal.com. We thank you for watching today and hope you'll join us next time on Frequency Matters.